thickness. Now we will proceed further. It is defined as that distance from the boundary in which the velocity reaches us 99% of the mainstream velocity. When you study in the class, at that time you know that due to the shear stress, the velocity is zero at the contact point and maximum at the center point. This is index. So thickness gradually increases. Nominal thickness gives an approximate value of the boundary layer thickness. For greater accuracy, the boundary layer thickness is defined in terms of certain mathematical expressions, which are the measure of the effect of boundary layer on the flow. Displacement thickness, momentum thickness, energy thickness, shape factor, in which the displacement thickness delta, it is defined as the distance measured perpendicular from the actual boundary such that the discharge through this distance is equal to the reduction in discharge due to boundary layer formation. Figure shows that it is 0.99 on increasing. Let u is equal to free stream velocity over plate. B is the width of the plate as shown in the finger. Consider a small elemental strip of the thickness dy at a distance y from the plate as shown in the figure. Let u be the velocity of the elemental strip. Mass flow per unit time through the strip if plate is pressed is equal to rho into area of the strip into velocity at strip, which is equal to rho into dy into b into u. Therefore, mass flow per unit time through the strip if no plate is placed, u equal to rho into area of the strip into velocity at strip when the plate is absent, and which is equal to rho into dy reduction in mass flow per unit time through the strip due to the insertion of the plate is given by rho dy into b into capital U bracket complete minus into another bracket rho into dy into b into small u bracket complete, which implies that rho dy into b into u minus u equal to rho into b u minus u into dy. Therefore, total reduction in mass flow per unit time for whole boundary layer equal to integral 0 to delta rho into b into u minus u into dy. If the boundary is displaced by distance of the displacement thickness delta and velocity of the flow is capital U, then the mass flow per unit time through delta equal to rho into area into velocity equal to rho as per the definition of displacement thickness. Equation number 5 is equal to equation number 4. Therefore, rho into b into delta cap into u equal to integral of 0 to delta rho b into u minus u into dy. Therefore, rho into b delta cap into capital U equal to rho b 0 to integral 0 to delta u minus u into dy. Therefore, delta cap equal to integral of 0 to delta into bracket capital U minus small u divided by capital U into dy. Therefore, delta cap equal to 0 to delta into bracket 1 minus momentum thickness theta. It is defined as the distance measured perpendicular from the actual boundary such that the momentum through this distance equal to the reduction in momentum due to the boundary layer formation. Therefore, let capital U equal to pristine velocity over plate, small b equal to width of the plate. Consider a small elemental strip of thickness dy at a distance y from the plate. Let small u equal to velocity of the elemental strip. Different conventions. Therefore, momentum of fluid per unit time through strip plate is placed equal to mass per unit time into velocity at strip equal to rho into dy into b into small u bracket complete into small u. Therefore, momentum of the fluid per unit time through the strip if no plate is placed, that is small u equal to capital U equal to mass per unit time into velocity at strip when the plate is absent equal to the bracket rho into dy into b into small u bracket complete into capital U. Hence, the reduction in momentum of the fluid per unit time through the strip due to the insertion of the plate is rho into dy into b into small u to capital U minus into bracket rho into dy into b into small u bracket complete equal to rho dy into b into u into bracket capital U minus small u equal to rho bu into u minus u into dy. The total reduction in momentum of the fluid per unit time for whole boundary layer equal to integral 0 to delta rho bu into u minus u into dy. If the boundary is displaced by distance of momentum thickness theta and velocity is pristine velocity u, then momentum of the fluid per unit time through the momentum thickness theta is given by mass per unit time through theta into velocity equal to into bracket rho b into theta into u capital U into capital U, which is equal to rho b into theta into capital U